Alright, so don't forget you have a test a week from today. Forgot to mention that. Monday. And it'll be, you'll take yours at the same time you took your last test, okay? So I'll resend out the spreadsheet if you forgot when you took it. Alright, number 7 reads, another component of acid rain is nitric acid, which forms when NO2, also a pollutant, reacts with oxygen and water according to this equation. The generation of electricity used by a medium-sized home produces about 16 kilograms of NO2. 16 kilograms NO2 per year. Assuming you have enough oxygen and water, what mass of nitric acid will form in kilograms? Alright, so I thought on Friday we were all on the same page and y'all, or whoever was here Friday, knew what I was doing. But after class, several people asked questions. So, let me break this down. The only way I can relate a reactant to a product or a reactant to another reactant is through the balanced equation. So the first step should always be to balance the equation. In these examples, I've already balanced them to save time. So the only relationship we're looking for here is the relationship between NO2 and HNO3. That relationship is for every 4 moles of NO2, I'm going to produce 4 moles of HNO3. Right, so if I wrote this out kind of just as a guide of the steps I was going to follow. Well, first off, I've got to get NO2 to grams. I don't want it in kilograms. So that I can use the molar mass of NO2 to get this to moles. So, NO2. Once I can convert kilograms to moles, then I can use this new relationship and I can go to moles of HNO3. From moles, I can always get to grams. And then if I have grams, all I have to do is do the gram to kilogram conversion and I'll get kilograms. Okay, so those are all the different steps that we'll go through. Okay, so I'm going to start with what I've given. That is 16 kilograms of NO2. Okay, according to what I wrote up here, the next thing I got to do is convert kilograms to grams. Then I go grams to moles. So I've got to find NO's molar mass, NO2's molar mass. So that's nitrogen plus 2 times oxygen. And that'll give me 46.01 grams NO2 per 1 mole of NO2. Okay, so now I'm at moles of NO2. This is where I can relate NO2 to HNO3. You could reduce this to 1 to 1 since they're both 4, but I'm going to leave it as 4 just in case you go back later, look at this example, Wonder where I got these numbers from. Okay, now I'm at moles of HNO3. Next thing, find molar mass, and I can convert that mole to gram. Molar mass of HNO3. I found the molar mass to be 63.02 grams. And lastly, gram to kilogram conversion. So type it in your calculator. Anybody got an answer? Yeah. .9 kilograms of HNO3. Any questions? We all got this? Molar mass of HNO3. Okay. You'll skip down to the bottom of page 3. It talks about the limiting reactant and theoretical yield. Okay, so in all of these example problems that we've done so far, it always said assume there is enough, in this case, O2 and H2O to react with NO2. Okay. Reason they did that is because there's always a limiting reactant or a limiting reagent, however you prefer to call it, in an equation. It's going to limit the amount of product you form, okay? So you'll always have a limiting reactant and an excess reactant or excess reactants. In this case, there were two of them. There were water and O2. So whatever the limiting reactant produces is called the theoretical yield. So it's the amount of product that can be made in a chemical reaction based on the amount of limiting reactant you have present. Okay, then the actual yield is the amount of product that you actually made if I were to go into a lab and perform the experiment. So with theoretical and actual yield, we calculate something called percent yield. It's not the same as percent error or percent recovery that we've done in lab. It's simply the actual yield over your theoretical yield times 100. Whew. Okay, let's look at some examples. So let's flip over to example 8. Okay, so there's the equation. There is a typo. In NH3, the 3 was big. It should be a subscript of 3 there. Okay, so it says ammonia, which is NH3, can be synthesized using this reaction. If you start with 86.3 grams of NO, 86.3 grams of NO, 25.6 grams of H2, find the theoretical yield of ammonia in grams. All right, so this is actually a two-step problem. Okay. Anytime you get a problem like this, it should always tell you what product you're interested in, so that when you solve for your limiting reactant, you go ahead and solve for your theoretical yield. Okay. So what we have to do here is we've got to take grams of NO to grams of NH3. Then we've got to take grams of H2 to grams of NH3. Whichever produces the smallest amount, that reactant is your limiting reactant, and the amount is your theoretical yield. Sometimes I get asked, well, isn't the limiting reactant just the one that has the smallest amount of grams? No, that's not always the case. Sometimes it might be, but not always. So we actually have to work it out. All right, so let's see if we can do this. So let's start with our 86.3 grams of NO. I want to get this to moles so that I can use the mole to mole ratio from the equation. So the molar mass of NO, 30.01 grams. This is a really good blue marker. Alright, once I have moles, now I use the mole to mole ratio from my equation. So for every 2 moles of NO, I produce 2 moles of ammonia. And I'm going to go ahead and convert moles of ammonia to grams of ammonia using the molar mass. So what do we get when we plug this in? Yes. And for whatever reason, I rounded it to 49.0. You can keep it however you want. Alright, so that's one step of this problem. Now we've got to do the exact same thing, but this time we've got to start with the other reactant. So this time I'm going to start with 25.6 grams of H2. but I'm following the exact same steps. So I need to convert grams of H2 to moles. Then once I get moles, I'm going to use the mole to mole ratio. Then convert moles of ammonia into grams of ammonia. And solve. I got 86.5 grams ammonia. Alright, so now I look at these two numbers. The smallest one, so this 49, this is my theoretical yield. That is how much ammonia I should produce if I went in the lab and I started with these two amounts of reactants and everything went perfectly. That's what I should get. Because this is the theoretical yield, NO is the limiting reactant. It limits how much product I can form. Therefore, H2 is the excess reactant. So I have more than enough to produce the 49 grams that I'm limited by. Does this make sense? Yes.
Did you get like that?
So whatever reactant produces the smallest amount, that is your limiting reactant. Okay. Yes. All right, y'all try number 9. I catch my breath. Alright, let's look at it together. Same thing as we did in the last problem. This time we are just starting with kilogram, ending with kilogram again. So I'm going to go kilograms of H2 to kilograms of NH3. Then I'm going to go kilograms of N2 to kilograms of NH3. Okay, so let's start with what we're given. 5.22 kilograms of H2. I need to convert that to grams. Once I get it in grams, I'm going to use the molar mass to get it to moles. 0.06 grams per 1 mole. And I look at the mole to mole ratio. For every 3 moles of H2, I produce 2 moles of NH3. Then convert moles of NH3 to grams. Then convert it to kilograms. For this one, I got 2.94 times 10 to the 4th I'm sorry, no, that's not what I got in kilograms. 29.4 kilograms of NH3. Did I get that for that one? Alright, let's do the next one. This time I start with 31.5 kilograms of N2. Kilogram to gram, then grams of N2 to moles, then mole to mole ratio, 1 mole N2 yields 2 moles of NH3, and 1 mole of NH3 is 17.03 grams NH3, and convert to kilograms. And let's see, we get 38.3 kilograms NH3. Right, so the 29.4 kilograms of NH3 is going to be my theoretical yield. Therefore, H2 is the limiting reactant. And N2 is excess reactant. Everybody good? Good, good, good. Okay, let's look at 10. In 10, we're going to take it one step further, and we're going to actually calculate our percent. So we're going to do the exact same thing that we've been doing. We're going to find our theoretical yield. Then from there, we'll calculate percent yield. Alright, it says we can obtain titanium from its oxide according to this equation when 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium 4 oxide. It says 42.8 kilograms of titanium is produced. 0.8 kilograms. anytime you're given a gram amount of your product, any one product, it doesn't matter, that is your actual yield. Because you can always solve your theoretical yield mathematically. You cannot solve your actual yield unless you actually went into lab. So that's always given to you. Alright, so then the problem says find limiting reactant theoretical yield in kilograms and percent yield. So, also always use the problem to determine which product you're solving for, okay? It didn't say specifically that you needed to solve for the theoretical yield of titanium, but it told you how much titanium was produced. That tells you, okay, I need to solve for the theoretical yield of titanium. I don't care about CO. Okay, so we're going to go kilograms of TiO2 to kilograms of Ti, and then kilograms of C to kilograms of Ti. So I'll write, I won't talk. I'll let y'all try to set this up as I do it as well. When you get done, check your answers. So it asks for a theoretical yield. For my theoretical yield, I got 52.9 kilograms of titanium, meaning TiO2 is my limiting reactant. Now I have to do the next part. Right, so the next part is to calculate the percent yield. So it's actual over theoretical. Your actual will always be smaller than your theoretical times 100. So you should never get over 100%. If you do, you've violated the law of conservation of mass. Alright, so I'm going to plug in the actual yield, which was given to me. Divide that by my theoretical yield. Multiply by 100. For my percent yield, I got 80.9%. If you're good here, go ahead and skip over to number 11. That's where I'm going next. Can I erase what I have here? Everybody good here? Alright, I'm gonna let you try number 11, but I'll be working it on the board so that we don't run out of time. when you get done, check your answer. While y'all are finishing up, let me talk for a second. So all I have left in this chapter is dealing with the excess reactant. So I'll post that as Wednesday's lecture, and then on Friday we'll review for the exam, and I'll work any questions anybody brings me. I highly suggest working all the book problems for both chapter 5 and 7. I don't know if you normally work the book problems, you might notice that on the test, sometimes I pick some of the book problems as test questions. And there's also extra practice on Moodle. Okay, so I'll be emailing y'all with the last part of chapter 7.